We have two components for today's program coming up. Abdullah is back for the last session of quantum error correction. And then we look forward to having you stay at the end for final words from the team and from you, because we look forward to hearing your ideas, your thoughts, your experiences, and your feedback. Abdullah, we just had a superconducting quantum computing lab tour video from MIT. And briefly, it was mentioned bosonic error correction and surface codes. Can you share something about that?
Sure. Hi. Hello, everyone. So what we are studying in this course is what is called qubit error correction, where the information that we are trying to correct or protect from noise is in the form of k qubits, right? But that's not the only way quantum physical systems can be. There are other kinds of systems, especially so qubit systems are in particular discrete systems because there's only a discrete quantity of them, and there's a discrete Hilbert space associated with them. But you can have infinite Hilbert space based physical systems, and for those you need bosonic quantum error correction. Then the other thing was surface code. So coming back to qubit error correction, the most famous error correcting codes right now, and right now probably the most practical ones are a type of error correcting codes called surface codes. They are actually stabilizer codes, right? So last time we looked at the basics of stabilizer codes, and surface codes are actually just particular types of stabilizer codes with some additional properties which makes them really nice to work with, and then have actually very good performance.
Thank you for building this bridge, Abdullah. And then it's time to dive into your content.
Sure, absolutely. So I hope everybody is ready. Let me make sure I am on the correct channel here. Live questions. Okay, so I guess my first question is to you. Do you have a question from last time? Jeff Thompson also mentioned erasure conversion surface codes in neural atom quantum computing. Yeah, so most people are, like most companies, are actually trying to implement surface codes. That's where that's kind of like the gold standard right now. But yeah, so I see, well, Pablo wants a recap. I will definitely give a recap. I think that's quite important. How is error mitigation different from error correction? Okay, so error mitigation. So error correction, as we saw, was the idea that you set up your you encode your information in a way that if errors occur, you can correct them, right? That's the kind of the code, that you allow errors to happen. You know errors will happen, so you allow errors to happen, but then you correct them, right? You send the information through your channel in a way that correction works. The other thing is to actually do things in a way where errors are reduced, and by doing things not at the hardware level where you're improving your hardware and making it less noisy, but at the software level you do things in a way that errors don't like either errors don't occur or the effects of those errors are mitigated. So I mean, error mitigation is like is also like a broad field, so there are like different things that happen with it. Yeah. Can we have a recording of last session? Yes, Marlo, please. People are asking. Oh, okay. So we do have, I think people could not find this before. Can we ask questions about stack? Absolutely. Please do ask questions about stack and let me know where the confusion is the problem. About LDPC codes, low density parity check codes, it seems like they're far more efficient. Any views? So yes, so LDPC codes are very efficient, and as it turns out, surface codes are a type of LDPC codes. They're not the best kind of LDPC codes, but they're definitely LDPC. There are people looking at trying to construct even better LDPC codes than surface codes. Is error correction applied immediately after gate, or is it made into the design implementation of a gate? What we have been studying till now is error correction, which applies more to communication or memory scenarios, where your Alice and Bob are communicating from a distance and there is noise in the middle, or you store something on a quantum hard drive, and then afterwards you want to read it and you want to see what like you want to make sure that the information on the other end in both cases actually is correct. But if you want to try to do computation with on noisy hardware, that is the regime of fault-tolerant quantum computing. We are not doing this in this workshop, but you know, that's a more advanced kind of area. You have to do more things there, and in that case, error correction is indeed applied immediately after every gate, and is indeed applied after every identity gate. So you have to sort of continuously do error correction over and over and over again. So most of the time in your circuit, you're actually just doing error correction to make sure that errors get removed. Okay, so is there a way to iterate over circ sample method? It doesn't seem to work as a normal list. Oh, sorry. So circ sample is actually just so this at this point I can probably share my screen, and what I can do is, oh God, let me just, so somebody, well, okay, so actually hold that question and I will answer the question about sampling at that point. Yeah, we need some literature references on Steam codes. There's, I will see what I can do. How many codes are there? Is there any way to sort a general? There are basically infinite number of codes, because n can go to infinity, and the number of codes that you can construct inside inside a n qubit Hilbert space are actually quite dense. So there's a lot of freedom. There's no general strategy to find new ones. There are specific strategies to find codes of certain types, and that sometimes helps, sometimes does not. Usually the errors come are constructed by humans being clever rather than some systematic algorithmic process. I'm not an expert in error mitigation, so I cannot answer the question by Pablo. Okay, so at this point, I'm going to kind of switch to like actually talking about the stuff, and then perhaps you can, some of these questions we can take at the end. Can quantum processor makers implement the QC codes inside their hardware? Yes, people are trying to do that. Google is probably doing the best thing right now. They have a couple of papers showing that their error correction works very well and is quite good. So yes, people are doing it. Yes, the correction is attempted at Bob. So let's go here. So remember, this is always our model, right? So there's Alice sending information to Bob. This is the problem we're trying to solve. Any problem that can be mapped onto this problem, we can solve. Any problem which cannot be mapped onto this problem, we are not solving at the moment. There's probably a solution to it, but you'll probably see that later. Okay, so I'm just going to start from here. So our goal was to systematically build quantum error correcting codes, and we were working in this model of Alice encoding and sending information to Bob, who then decodes it. And our goal when we said that we want to build quantum error correcting codes is what we wanted was a consistent way of constructing an encoding and decoding procedure, which in fact it's self-constructed of the syndrome measurements and a decoding process to go from the corrected code word to the estimated message. And we also wanted to construct logical gates. To this end, we ended up constructing stabilizer codes. So the idea was that we had the poly group. The poly group was the on n qubits. So the poly group on n qubits was the set of all n-fold tensor products of poly operators, right? And within that group, we had subsets of or subgroups that we called stabilizer groups themselves. And stabilizer groups had this additional property that every element in them commuted, right? So if you took any two elements in S and you tried to compute the commutator for them, you would find out that they commute. And the other property was that -I was not inside this subgroup. And the way to construct codes, stabilizer codes, using once you have identified this S inside or picked chosen an S inside your poly group, was that this S told you how to do your encoding and decoding, right? So remember that our abstract description of a quantum code was that we had the Hilbert space of k qubits, also called the message space, and we mapped it onto this subspace of n qubits, which we call the code. And I mean, obviously, I mean, this is k qubit, so this space has dimension 2 to the k. Obviously, this subspace also has dimension 2 to the k, right? So these, I mean, in technical language, these two spaces are isomorphic to each other, which is why we can do the encoding. The idea was that if you had, for example, this repetition code, it was a stabilizer group with 4 elements, but it also had only 2 generators, which meant that you could take these 2 elements, not unique set of elements. You could pick different other subset as well. You could take these guys, and if you multiplied them together, you could construct the other 2 elements. So these were the generators of S. And the idea was that if you wanted to construct the encoding, all you did was that you constructed the simultaneous stabilized states of these generators. So generators are always finite. So if you have m generators, you can, as you learn in the notebooks, you can construct groups of size 2 to the m, right? So for example, there are 2 generators here, so 2 square is actually 4, which is why there are 4 elements here. So you actually have only a small set of generators for any stabilizer group, and computing the simultaneous stabilized states is quite easy. So you can just do that and find out, construct something like this. And then the other thing that we figured out was how to do syndrome measurements. So the syndrome measurement idea was that we basically like measure each of our generators, and we already figured out how to do that as well in a previous notebook. Is that you if these are your the first 3 qubits are your code state qubits, then to measure it, basically you apply a Hadamard gate to your ancilla qubit, which from now on I'll call the syndrome qubits. So I'll apply a Hadamard to syndrome qubits, then do these controlled Z operations. So whatever the polygate here is, I do a controlled operation from that to that. So if this was an X, I would do control X. And if this was, for example, a Y, then I would do a control Y. And I would do these, and then I'll apply a Hadamard to that syndrome qubit as well. So that would be my first measurement of the first generator operator. And then I could also do that similarly for each generator that I had. And then I do actual physical measurements over here, which allows me to actually figure out what the syndrome is. So this is how stabilizer codes work. But what we want to do today is kind of dive deeper into them. So let's see if there are more questions. Okay, so people are talking about something else, so I will. Yeah. So quantum error correction, lecture 4. Today we have these. Sorry, I didn't plug in my tablet. So these are the notebooks for today. There's a optional one, decoding. It's not that important. I mean, encoding is generally more important. Syndrome measurements are more important than decoding. So don't worry about it if you don't find time to do the decoding notebook. Important message. Please re-download repository. I have made corrections. So people send corrections, or I look at them myself, and then I do the corrections. So please re-download it, so you get the latest version. Okay, so there are four things we are doing today, right? So we are going to construct what is called the vector form of Pauli operators in the generator matrix, and then we are going to use this vector form to construct the encoding circuits and syndrome measurement, right? So last time we had the more abstract procedure, but this time we're actually going to try to get into the algorithms of it. How do we do all of this in Python, kind of deal, and have efficient and nice algorithms for it that work for anything. So yeah, so random questions in chat. Anyway, so vector form of Pauli operators. So the idea is that we don't want to write the IXYZ or tensor products of IXYZ all the time, especially in software. This is quite hard. So what we're going to do is we are going to map these guys to vectors and make it kind of simple. So what we do is we say that I is actually equal to this vector of length 2, right? And there's a line in the middle just to distinguish between the left part and the right part. So just to kind of specify, this is the X part, right? And this is the Z part, right, on the right side of the line. And you can see immediately what it means, that when you have X, you put a 1 on the X side and you put a 0 on the Z part side. Z, on the other hand, you put a 0 on the X part and Z and 1 on the Z part, right? And then Y, which is obviously equal to XZ, is going to be is going to be 1 1, because it has both of them. So important message here, which I'm going to put and write over here, is we will ignore phases from now on. So if phases are not important, right? You will see that in the description for the encoding, or the example of the description of the encoding for the repetition code that I just showed, or the syndrome measurements, there was no role of the phases. So I should particularly write that, for example, this is if I have, for example, minus X, I will still continue to write 1 0. If I have I mean, if I have iota, well, plus minus iota X, I will still use 1 0 as the representative. Okay. So for all of these, I will just ignore the phase and just write them like this. Yeah. So I mean, this is quite simple. What happens in the 2-qubit case? So tensor products. So if I have, for example, X tensor Z, so what I will do is I will use these guys to build a larger vector. So now there are two of these guys. So I will have a vector of length 2n, vector of length 2n. So I will just use this. I will say 1, 0, 0, 1, right? So you can see that this one is this one, this 0 is this 0, and then the second guy, this 0 is this 0, and this 1 is this 1, right? So it should be clear. If I have, for example, identity y, then I get 0, 1, 0, 1, right? So this is quite simple. So if I have x tensor y tensor z, then I'll construct even a longer one. So I mean, the way I write them is I look at them and see. So there's a x here, so I put a 1 here. There's a y here, so I put a 1 here. There's a z here, so I put a 0 here. Then I write the z part. I have an x here, so I put a 0. I have a y here, so there's a z inside y, so I'll put that. There's a z inside z, so I'll put a 1 here. Right. So this is the kind of vector form for the operators. This is easy to write in Python, etc., and do computation with. So which I'll show you in the next slide. But any confusion about this vector form for the operators? So please let me know in chat if there's a problem. Otherwise, we can move on to the next thing. XY is Ron asked XY is addition. Yeah, we will exactly see that. Didn't get the third product. Your trick is to identify the result. So Dhaval is asking. So I mean, remember that I have to write down the x part, right? So this is the x part. This is the z part. X part, z part, right? So I will read this entire string once, and I will put a 1 wherever there's an x or a y, right? In the x part, then I read the string again, and wherever there's a y or a z, I'll put a 1, right? So I go here and I see 1, 1, 0, right? That's the first string. Then I write the z part. I write like 0, 1, 1. That's over here. So I don't see a lot of questions. So I mean, this will become clear as we do more examples. But let's do some examples, or well, further things, why this is useful. So the first thing that is useful is that we can multiply operators, as somebody has already identified. So multiplying operators is equal to adding their vectors. Okay, so we already identified that xz is y, right? Again, up to phase. I'm ignoring phase, so this is this. So that is equal to 1, 0 plus 0, 1, right? This is x, this is z, and then when I equal to, I get 1, 1, which is y. Is this the simplified lesson set poly can be simplified? I'm not quite sure what you mean by the question. So anyway, you kind of see how this works. So we can do this at a with the tensor product structure as well. So if I have x tensor z, yeah. So let's do this. Let's do x tensor y. Okay. So I know that this guy is actually 1001, right? And this guy is 11. I should put guys, that's clear. And then 01, right? And then when I add these guys up, so one, remember we are doing modular 2 addition, right? So maybe I should put a 2 here to remind ourselves that we're doing modular 2 addition. So 1 plus 1 is 0, 0 plus 1 is 1, 0 plus 0 is 0, and 1 plus 1 is 0, right? And that's exactly what you get, right? Remember, x into x is identity, and z into y is actually just x. And sorry, and you can see this is exactly what it is, right? So identity on the first guy and x on the second guy. So I'll let you convince yourself that this kind of works in for every possible case. You just have to check all the additions once, and then things will work. So yeah, so this is exactly what we're doing, Valerie. We took something big and then we simplified it into this thing. What do we mean by representing operators as vectors with space? So I mean, Raza, these are, I mean, just to be super clear, I mean, these are not like your states. These are still your these are still operators, but we are going to write them as vectors so that we can do some run some algorithms on them very easily. That's all. They are still operators. This is still a poly operator. It's just written in a different way. Remember that writing things in a different way does not change their intrinsic nature. What you should convince yourself, for example, is interesting, is that, for example, you can see that, I mean, I've given you, I told you that multiplying operators is actually equal to adding their vectors, right? So, I mean, a good thing to notice is that we discussed last time that multiplying I, X, Y, Z with each other only produces I, X, Y, Z. It doesn't produce any new operators, right? And then you can see very easily here that just adding these guys up in any combination, modular 2, just produces these vectors and nothing else. So this is actually quite a this is a correct representation that completely correctly represents these operators and nothing else. So we are writing the operators as operations to do as vectors to do faster multiplications. Yes, that's exactly it. And so we can do things systematically. Yes. Yes. I mean, we say that I'm concatenating two vectors together, but you can read it however you want. I like a nicer way of saying it is that there's the X part and the Z part, and we are putting them together. Yeah. So I don't, Ismail is writing something, but I'll go on to the next thing. So I think it should be clear. Like you should convince yourself that this multiplying operators and adding their vectors is the same thing, and you just have to check each of the possibilities. If you, and there are only a finite number of possibilities, check all of them, and you'll convince yourself that it works. Now, the next thing that we want to do is commutation relations, right? So remember that commutation relations meant that we were asking ourselves a question that given P comma Q in in the poly group of n operators, we wanted to ask is P equal sorry, PQ equals to QP, or PQ is equals to minus QP, right? This was our question. and this meant the first thing means that they commute, and the second thing means that they anti-commute, right? Depending on what the result is. And we had some examples of this as well. So, for example, sorry, let's do this. XX is actually equal to XX, right? Writing in the opposite way. So these commute, for example, but X tensor Z and Z tensor I is actually equal to minus of Z tensor I X tensor Z. So these guys anti-commute. Right. So I mean, you can do these detailed multiplications later on if you don't believe me, but Isma is asking, I'm a bit confused about what you're saying, X part and Z part. I mean, do these X and Z refer to the polymatrix X and Z? Kind of. So X part is just the left part. I mean, it might be easier to say the left part of the of this matrix and the right part, right? So left part and right part. The left part, a zero in the left part, a zero means that the corresponding operator had an identity or a Z in that location, and a 1 means that our operator has either a X or a Y in that location, right? On the Z, in the Z part or the right part, we are asking ourselves the opposite question. At the ith location inside the Z part, if there is a identity or an X, we put a 0, and if it's a Y or a Z, we put a 1. Yeah, okay. So commutation relations. So for that, we just need this symplectic inner product. So the idea is that now we are saying that any polymatrix tensor product, however long, is some P1, which can be written as this A concatenated with B, right? And to use the language of one of you guys, and P2 is just C concatenated with D, right? So these are, if P1 and P2 are tensor product of n the polymatrices, right? Or they belong to the nth polygroup, then these vectors are of length 2n, right? Both of these are of 2n. And what we can do is we can construct a special type of inner product between them, which is called the symplectic inner product, which is defined to be this. Okay, so this is a definition. Okay, and the idea is that the symplectic inner product between P1 and P2, given by written like this, P1 dot P2, is actually, let me just replace these guys with red. So this is the ordinary dot product. Mod 2. Okay. So what I'm saying is that if we want to construct the symplectic inner product between them, which gives a number as the output, so I take the X part over here, and I take the ordinary dot product with D. Okay. And then I take the second part of P1 and I multiply it with the first part of P2, right? That's P dot C, and this is ordinary dot product. So, for example, let us do some examples here. So, let's see. Let's do this. We also need that. this is true, xz is actually equal to minus zx. So let's do all of these examples. Well, yeah, so I want to do, well, so what we have is this additional lemma that that if they commute, then p1 dot p2 will be equal to 0. And if these two guys, oh, there's a mistake here that I need to correct. Anti-commute. So, right. So, sorry. And which way is it? I want to be sure that if p1 and p2 come, well, I'm pretty sure the second one is anti-commute, but what will happen is we'll check right now and we'll confirm. So let's do a whole bunch of these symplectic products, and we will see what the result is. Okay. So example 1, p1 is equals to x, which is 1 0. Okay. p2 is equal to z, which is 0 1. Right. Actually, let's write it like this. Okay. I'm going to construct the symplectic product between them. So p1 dot p2 is going to be the first guy part of x, and let me use the red dot to indicate an ordinary dot product, and the second part of p2 plus the second part of p1 and the first part of p2. And this obviously 1 dot 1 is actually just 1 mod 2 plus 0 dot 0 is actually 0 just mod 2, and this is equal to 1. So yeah, so you can see that p1 x and z anti-commute with each other, right? And their symplectic inner product is actually equal to 1. I hope this kind of works. Let's do a more involved example. So we have x tensor z. The representation of x tensor z is actually just 1 0 0 1, and z tensor I is actually, you can see, is what? I mean, maybe I should ask you instead of, what is z tensor I? So remember, there are two guys here, right? So I will have a vector of length 4, 2 on the x side, 2 on the z side. So Bakao is, well, so I get something from Mohammad Raza. X on the left, Z on the right. So a lot of people are getting it reverse. Remember that on the left, we have the X side, and on the right, we have the Z side. So we only have Z operator here, right? So the 1 will be on the right side, which is the Z side. 0 0 1 0, right? Indicating that the first guy is a Z, right? So I look at this guy and this guy. This is a 0 1, which tells me this is Z, and this guy and this guy is 0, which tells me this is the identity, right? Which is exactly what I get over here. Does this make sense to everyone who got? Yeah. So we are doing Z tensor I. X tensor Z is this guy, Z tensor I is this guy. So P1 dot P2 is going to be, again, I'm going to take this guy and multiply it with this guy. 1, 0, 1, 0, plus 0, 1, 0, 0. And what I have is an ordinary dot product, which is I'm representing with a red dot, right? So the black dot is a symplectic inner product, and the red dot is a ordinary dot product. So this you can see is 1 into 1, which is 1, plus 0 into 0, which is a 0. And on this side, I have a 0 into 0, which is 0, 1 into a 0, which is also 0, right? And this whole thing comes out to be 1. So anti-commute. Right? This was also an anti-commute. So again, in the notebooks, there's a little bit more reasoning, and you should actually convince yourself that things work like this. And indeed, the symplectic inner product does do these commutation relations. Let's do one more example. I think so you were familiar with things. So last time we said that X tensor X, we did this example particularly, Z tensor Z is actually equal to Z tensor Z X tensor X. Okay, so this is the commute, right? Because there were two minus signs that we got, and those minus signs cancel each other out. That is why there's an overall plus sign, which makes them commute. So now my P1 is actually X tensor X, and P2 is Z tensor Z. This is equal to, now everybody should know. And well, first tell me this guy, and then we'll do the other one. What is X tensor X in vectors? Yeah, good. So now everybody's caught on. 1, 1, 0, 0. And then what is Z tensor Z? It's obviously the opposite thing, right? So 1, 1, right? Yeah. So yeah, good. So I think people are catching on. So now we do P1 dot P2, which is equal to, we can see, is going to be 1, 1, 1, 1, plus 0, 0, 0, 0, and we have a dot product in the middle. So you can see this is 1 into 1, which is 1, plus 1 into 1, which is 1, plus 0 plus 0, right? This is 2, and then obviously we are doing everything mod 2, so this is actually equal to 1. Sorry, this is equal to 0. So which tells me that they commute. So I'll tell you the intuition of why this works. And the intuition is exactly present in this example. We know that X and Z anti-commute, right? We did that over here, right? X and Z anti-commute. So if you have in your larger tensor product structure, whenever there is an X and a Z in the same location, right? There's X in the ith location of the first operator, there's X, and in the ith location of the second operator, there's Z, right? Those guys will give you a minus sign. But then if you have an X and a Z at the same location and an X and a Z at some other location, those two minus signs will cancel out and you'll get an overall plus sign, right? This is this 1 plus 1. that it's saying that there are two locations where X and Z coincide in the two operators, and those minus signs are canceling out, so you actually end up getting a plus sign, which is commute. So basically, these commutation relations between these poly operators reduces to checking where the X and Z operators coincide. And when I say X and Z, I also mean including Y. Y acts as both X and Z. So X, which is why X and Y anti-commute, and Z and Y anti-commute, right? So I mean, it should be quite easy to see, for example, over here that I mean, I can do another example. If my P1 is actually X tensor X and P2 is Y tensor Z, for example, then P1 dot P2 will actually still be 0, and they will commute. And again, the reason is that there are two locations where these anti-commuting operators interact with each other. So in the first location, there's anti-commuting operators. In the second location, there are anti-commuting operators. You get a 2 from 1 and 1 from both of them, which sums to 0. Okay. Yeah. Yeah. So Guillermo's question has been answered. That's great. Okay, so now we know this algebra of these operators, right? So we are saying that by mapping these our poly operators to these vectors, we can do everything. We can multiply them together, and we can do commutation relations. That's all we kind of need to do the kind of construction of stabilizer codes that we have. So let's go and like construct some, go back to codes and construct some further things. So this is actually quite simple, that generator matrix in vector notation or representation. So we take, okay. So the generator matrix of a stabilizer code is the matrix representation, is the matrix whose rows are the generators of the stabilizer group, right? Remember that we had a stabilizer group from which we were constructing the stabilizer code. The stabilizer code has so if I look at the generators of the stabilizer group and put them in a matrix, then I get the generator matrix. So for example, here's example of repetition code. Code for right. So we had this repetition code in which we had X tensor X tensor identity equals to 1 1 0 0 0 0, right? You can see that this is the correct representation, right? On the X side, I have 1 and 1 in the first two locations, and then for this guy IXX, I put a 0 1 1 here. So, and then I can just put this in the form of a matrix, in this augmented matrix where there's a X side and a Z side. Yeah. So if I show you other codes and examples, you will be able to recognize this. Any confusion about this? Remember, the reason we are doing all of this, we are only looking at the generators, is that the encoding and the syndrome measurements, and also decoding and everything else, everything that you want to do can always be done in terms of the generators. We don't need to know all the elements of the stabilizer group for, well, pretty much all operations. Some operations you do need, but for most operations that you actually like are working with, you just need the generators. So we just put the generators of the stabilizer group into this matrix. I'm still here. Did I get disconnected?
For me, you're good, Abdullah.
Yeah. Okay. Good. So, any questions about this thing? We'll look at more examples just about now. I'll show you. But any confusion about this? That we are taking the generators of my stabilizer group, right? So I can put some more context that had two generators. And remember, this is not unique. I should say this, right? That we said the generators are not unique. You could pick for the repetition code. You had several choices. You had three different choices of generators, pairs of two operators that you could pick that could create any other operator in your group. And we chose this choice, and with this choice, the generator matrix is this. If we change our choice, our generator matrix will change, but actually that's the same thing because it doesn't really matter. Yeah. Okay, so Artemis is happy. This is wonderful. Yeah, that's exactly right. So now we are, instead of having to deal with poly operators in which it is hard to see the structure, we will now start to see structures in terms of these matrices with zeros and ones, because then we'll do algorithmic operations on these matrices and these vectors, and we'll get nice results out, which are easy to translate back to poly representations. So let's look at some examples. So we will go down and we will look at some common codes. Okay, so this is also a tutorial in Stack. So I think this is big enough. Actually, don't need this. So you can see that what I've done is generate a matrix for repetition code. So I have constructed a NumPy array. You can see that this is slightly hard to read with Python because there's no augmentation line in the middle. But if I draw, like highlight this, I think it's easier to see that I have x tensor identity, right? And then this is, you can see that the right-hand side is 0. So this is identity tensor x. And then in Stack, what we do is to construct the stabilizer code, we just pass this generator matrix to the code object. Okay. So I pass this and it creates a code object, which is a repetition code. So this code object has a bunch of nice things stored inside it. So I can ask ourselves, actually, we should do this ourselves. So before we look at this, so remember that the repetition code had n equal to 3, right? Because we were taking, well, it had k equals to 1, right? Because we were encoding 1 qubit of information with the repetition code, and we were encoding it into 3 qubits, right? Which is why there are 3 operators here. And we have m equals to number of generators. This is equal to 2. And there's a relationship n minus k equals to m. This relationship, okay, this always holds for stabilizer codes, right? So this is a critical relationship between stabilizer codes. Unfortunately, we do not have the time to do the mathematics for why this is true, but it comes down to how many stabilizer states you can construct with these generators. But you have the relationship that the number of So this I will refer to as the number of, this is actually, number of data qubits, and this is number of logical qubits. Okay, this is the terminology we'll use, that we are encoding one logical qubit into 3 data qubits. And our code has this number of generators, so n, k, and m. And n minus k will always be equal to m for stabilizer codes. This is a critical relationship that you should remember. Okay. In Python, you can write 110 plus 000 for the x part and the z part. Absolutely. You can do this. So now you can see that I have n inside stack, right? So all you do is you pass it a generator matrix, and or like, I mean, this is quite simple, that it recognizes that the number of data qubits is 3, the number of logical qubits is actually equal to 1, and the number of generators is actually equal to 2, right? That is the number of rows in my generator matrix. And then what I can always do is, I mean, if sometimes I have some large matrix and it's hard for me to read, then I can just ask it to print these polys. So I can do something like this. I can say, hey, print this generator matrix, and you can do this. I can also, I mean, there's a different way of doing this. You can see that there's print polys indexed as well, which gives me generator matrix. And then I can do it in an index form as well, right? This is quite useful if you have a large matrix, then you don't want to see a lot of i's, so you just write x0, x1, so x2. Okay, that's one thing. Then let's actually look at other codes. Okay, so stack already has some codes built into them, right? So so that you don't have to kind of look at the generator like extract things out or write down the generator matrix. So what you do is this slightly different notation here, right? So it has a module, common codes, and inside that it says, hey, create a code which is the 513 code, right? So what is 513 here? So I mean, for anyone who does not know, what is this? What are these numbers? If somebody knows. I see no one typing, or yeah. So they are K and D, right? So I should also write over here, just to remind ourselves that a code is described by N, K, D. The D is the distance. For now, we're not studying what the distance is. Okay, so you just have to believe me that the distance is whatever I tell you it is. So maybe some other time we can look at what it means. So going back here, you can see that this is a code where the first guy is n, 5n, k is 1, and the distance is 3. Okay, so I'm just going to ask stack to create this code for me, which is this. Which actually just leads to this guy. So this is a generator matrix. I mean, you can try to read it off. I mean, you can already see that it becomes harder to read. So, I mean, generally, we don't even have to read it for algorithmic purposes. We just process it in whatever way. But if you want to kind of see what it says, you just, you print it out and you can read out what it says. So this is actually quite a nice code. You can see that it has this XZZX feature, and then you can see what's the next guy. So XZZX. Then if you read it from the third entry, right? So here we started from the 0th entry, and we said XZZX. Here we start for the first entry, and we say XZZX. Now we start from the second entry, and we say XZZX, and then we start from the next entry, and we go XZZX. So it's actually a symmetric code where all the generators of the code, right? Remember, these are generators of the code. They are all basically the same operator where the matrices themselves are shifted by some amount. So if I can just print out, for example, the number of generators, the number of data qubits, the number of logical qubits. It's all here, right? So there are 4 of these guys. So M is actually 4, 5 and 1 you already know. Oh, so Pablo has an excellent question. Maybe I should have addressed this. Can stack get the parity check for that G any method? So this is something that you need to read this. So you'll read this paragraph and explain things. But this generator matrix, when I say this, is actually not equivalent to the generator matrix in classical codes. This is a really unfortunate terminology. This is actually, when I write G, this is actually the parity check. It is analogous to the parity check matrix in the classical case, but we call it the generator matrix because it is constructed from the generators of the stabilizer group. There is no H or corresponding matrix in the quantum core case. We only have one matrix, which is this matrix, the generator matrix, which is constructed from the rows of the whose rows are the generators of the code. That's all. We don't need another matrix. Everything we want to compute can be computed from this code, from this matrix. So I think this will be clear when you read it. Don't get confused right now. Right now, we just have G, whose rows are the generators of the code. So the next code that that's inbuilt into stack is the Steam code. So again, you just say 713, and it constructs the Steam code, and it's this guy. Remember the Hamming code? Right? So we did the Hamming code when we were doing classical, and this is actually the Hamming code. If you look at this guy, if you can see this generator matrix. The first 3 rows, or the first 3 generators, you can see on the right-hand side, there's only zeros here, which means the first 3 guys are only X-type generators, right? They only have X's in them. And the last 3 guys only have Z's in them, right? So the left part is 0, and there's only stuff on the right-hand side, which is why it's Z. But what is the sub-matrix or block matrix inside this? This is just the matrix of the Hamming code. If you go back and you compare, right? You go here and you you compare Hamming this matrix with this matrix, you'll see that's the same matrix up to some permutation of columns. I think I permuted the columns when I was copying this, but basically you get this. So what we do is we construct this code by taking a classical code and constructing, putting on the left side, and then taking that same matrix and putting on the right side. So this is a way that we can construct quantum codes. A lot of quantum codes are exactly this feature, where has this feature where we take a classical code and put it on the left and the right. There's some additional properties that these things have to obey for this to work, but the Hamming code does obey them, so it works. So just don't go about doing it for anything, but you have this structure. Okay, so you have something like this. Any so this is good. Okay, so now up till now we have only seen codes where k is equals to 1, which means that we are only encoding one logical qubit into our code, right? So here we are encoding one logical qubit into 7. But now what we want to do is we want to go bigger, and we want to set k greater than 1. So here's a 422 code. So here's this 422 code. it has these very simple structure of x, z, z, x, and y, x, x, y. So we talked about the surface codes, or we mentioned the surface code at the start of this conversation. And actually, this 422 code is actually the simplest surface code that you can construct. It's actually the trivial surface code which does nothing. So because the distance is actually too small, but I mean, it's still a surface code. Anyway, so I mean, the idea here is that there are now 2 logical qubits that you import into 4 data qubits. And if you want to go even bigger and construct a useful code, we have the 833 code, which takes 3 logical qubits and encodes them into k data qubits. So you can see that there are 5 rows here, right? Remember our fundamental relationship. So 8 columns here on the x side and 8 columns on the z side. 8 columns minus 5 rows gives me 3 logical qubits, right? So that consistency relation will always hold, and you'll get some, this is, I mean, in some complex or not very nice form, or not very symmetric form, but it does the job and it constructs something like this. So these are some common codes, and I mean, you can see that there's a conversion between the poly operators and the generator matrix in every case. And it's like we will work algorithmically with the generator matrix. Let's see if there are questions at this point. Mohammed is typing, so I will just wait for him. Anything else? Is there anything else that I can? Right, remember in Jupyter you can tab, or if you want to see everything that a stack related thing, you can always there, right? And it will tell you all the things that you can do with this object. So there's a whole bunch of these things. There's one important thing. I think you can, if you try to create your own code by doing this thing, right? So you create a generator matrix and you input into stack. One of the things that you should probably do is you should say, hey, cd rep dot check valid code, right? And it says true because this is a valid code. I can mess with this, I think, by, I think if I put a 1 here, then it's a false, right? So it will tell me that, and again, what's checking is that the what I gave you was actually creating a stabilizer group, and it's not creating a stabilizer group. So it told me which guys don't commute. So actually, I mean, this thing should be a check. I should fix that so that it should always do this check on its own. But this can also, but I mean, right now you can just do this and then it works. Yeah. So more than one logical qubit biopairs? No, so Mohammed, that's not, that's, you're seeing something that's not there. You can construct purely X and Z codes with more than one logical qubit. That's not a problem. Artem, we see so many different codes. How do we select the best code for various circuits? That's an excellent question, and there's no nice answer to this. Basically, you test it. Well, I mean, you'll build some intuition as you work with these things, but basically, ultimately, it boils down to actually testing and checking that, hey, this is my application. This is the code that will work best. So this is a wide problem and like quite difficult. Anyway, I'm actually I've taken a lot of time, so we have to move to the next few slides a little quickly, but it's also quite simple, and it's not difficult. So the next thing that we have to do now that we are familiar with some codes is that encoding circuits for stabilizer codes, right? So we need a procedure for this. And I'm just going to give you the overview, right? So there's a very nice notebook that goes through each of these steps in full detail. I'll just give you a very quick overview of what the essential elements are. And you'll do, like, there's all these algorithms and whatnot that lets you do everything. But so we had some generator matrix, right? So we have a generator matrix like this. Now, what we want to do to actually construct the encoding circuit is to bring it to standard form, right? So you can remember that we have this choice of generators, right? So given our stabilizer group, we can choose different subsets of it to act as our generators, as operators that construct the whole group by multiplication. But that's I mean, not every choice is nice for our algorithmic purposes. So the first step we always do is we bring our generator matrix to standard form. So how do we do it? What is the standard form? So there are three things that you can do that do not change things. So remember that, I mean, this is the easiest thing to remember. So let's, I mean, let the let S have generators G1, G2. Well, okay, that's dots GI, GJ, and GM, right? Remember that there are M generators, so I'll index this here, right? So there are M generators, and one of them I call I, and one of them I call J. Maybe, sorry, I'll make one correction, is that I've been zero indexing everywhere. So people are unhappy that sometimes I don't use zero indexing. So let's just zero index. So two of these are GI and GJ. So now notice that you can do three things. I can reindex GI to GJ, right? So I can say that what is GI is actually GJ and what is GJ is GI, right? I can always do that. That's just reindexing, right? Do you believe me that this works? And if you do believe me that this works, then what is the corresponding operation on the generator matrix if I do this reindexing? What am I doing on the generator matrix? Transposing, column transfer. What are the generators in the generator matrix? Are they the rows or the columns? No, they're rows, right? So this is the first generator, this is the second generator, right? There are two generators here. And this is my 0th generator, this is my first generator. I can say, oh no, I want this guy to be my 0th generator and this guy to my first generator. So what will I do? I'll just swap the rows. Yeah. So swapping rows. So swapping rows doesn't do anything, right? This is equivalent to swap rows of G. Okay, so nothing happens. Like if I just swap rows of G, it's still the same S, right? Nothing has changed. Another operation that I can do, so somebody was talking about what is swapping columns. So if I swap columns of G, what is that equal to? So maybe it's confusing because that's nothing is equal to swapping columns of G. But if I swap columns of both oh yeah, okay, of X part and Z part, well, in in X part and Z part simultaneously. Okay, what that means is I can say that I want to swap the second and the third column here and the second and the third column here. Right, so what will I do? If I take this second column and the third column here, that's equivalent to re-indexing the qubits. Right, so I'm just saying that I will what I'm calling my second qubit is actually my third qubit, and what is my third qubit is actually my second qubit. So I can re-index qubits. Okay, and here's the other thing. This I'll tell you, that I can construct a new generator set where I do this G0, Gi, Gj, Gj, Gm-1. So what I can do is I can take one of my generators and I can multiply it with some other generator. Okay, this will not change my S. Okay, so if S is generated by these guys, S will also be generated by these guys. You can go back to the arguments in the generator section to think about why this is true. We don't have a lot of time, but I mean, this is not difficult to understand that that if I multiply with an existing generator, I don't create a new group because the group is closed, right? So if I multiply with a generator, all I get is a new generator set, which is slightly different from the old generator set, but perhaps more useful in some way. So this operation is actually equivalent to adding rows of G, right? Remember, because multiplying operators is actually equal to adding the vectors, and adding the vectors are rows of G. So we just add 2 rows of G, which is equivalent to changing my generator set. Okay, so, and you can see that these operations, what are this? Adding rows, swapping columns. These are kind of things that you do when you're doing Gaussian reduction, right? If you remember your linear algebra, Gaussian reduction is just basically these kinds of operations, row and column operations. So what I do is that this is the standard form. So I have some G in which there is something here, there's something here, and I take it to my standard form, which is this way, where these are block matrices. Okay, so I, A1, A2, B, C1, C2, D, I, E2, they're all block submatrices, where this has R, rows, right? So this is M minus R rows. This is, well, let me write it below, R columns, right? So the first, this identity matrix, for example, is R rows into R columns, right? This is, oh God, okay, I have forgotten, so I have to remember. Over here. M minus R, yeah. So this is also M minus R columns, and this guy is N minus M minus plus R column. Oh, well, so No, sorry. Well, I mean, this works. We can argue about further thing. And then obviously, because the X part and the Z part are equivalent to each other, so this is also, I mean, I should write it on top. I mean, these blocks are R columns, this is M minus R columns, and this is N minus M plus R. So you don't actually have to do this by hand. The standard form stack has a function for doing this, but basically what you do is you do these green operations where you swap rows, you swap columns, you add rows, and ultimately you get into this form. What is this form? You can see that there's an identity here. There are some zeros here. There's identity here as well. And this you can't simplify further. But for example, G equals to 7, 1, 3 code has G equal to this, okay? And it had this structure, and then what you do is you reduce it down. So you can see there's an identity matrix here. The A1 is actually these three guys, I think, and then this last guy is A2, okay? And then I mean B, C1, C2 are all 0, but D is again is actually these three guys. Identity you can see is identity over here, and then E2 is actually equal to this. So how do you do this in stack? What you do is yeah, so you just ask stack. So let's just go through this. This is my 7313 code, and I say stack, hey, construct the standard form, and then you print it out. So you say, hey, the standard form is over here, standard generator matrix, and you just print it out, and you get exactly this thing, okay, that we just saw. So any questions about this? So it will become a lot clearer as you work through it yourself. But anyway, it's something like this, and this is probably the hard part. The easy part is what follows. So the next thing that we need to do, remember that we had to do logical operators for the code. So remember, what were the logical operators? You already have had some quizzes regarding this. That so you should know that logical operators are the poly operators that act like the logical poly operators on these things. So we need some operator that acts, which swaps the 0 encoded state with the 1 state, and we have some Z operator which puts a minus sign on the 1 encoded state. And actually, once you have the standard form, which stack gives you, then constructing the X and Z operators is quite simple. You just take various components of my standard generator matrix, and I put them in these ways, and I construct my X and Z operator. Okay, so I construct this, and an example of that is given in the notebook. So for this, exactly this, right? So to do this, you ask stack, hey, this is my code object dot construct logical operators, and I do this. It constructs the logical X. Remember that this K equals to 1. So you get a list of logical operators. If K was equals to 2 or something, or some larger number, then you would get a list of these logical X operators, one for each qubit. But here we only have one of these guys, and you can either write this vector form, or you can just print them out. So the what stack is telling us is that if I apply XXX on the last 3 qubits, that is equivalent to doing a logical X operation on my logical qubit. And if I do ZZI, ZZ on the first 2 and Z on the last guy, that is equivalent to doing a logical Z operation. I should mention at this point that logical operations, I think you've seen done an example of this as well, are not unique. So for example, a much more symmetric choice is something like this. So I can put X in all the guys, and I can put Z on all these guys, and that will create my logical X and logical Z operators as well. So I mean, there are different choices. These are more symmetric. These are smaller ones in some sense of the word. So it depends. You can apply any one of them if you choose. And then encoding circuit. So how does the encoding circuit work? So you have the standard form. From the standard form, you basically have there's an algorithm for it, given by the scientist Gottesman back in the 90s. Basically, you look at various pieces of this and you apply gates to it. So basically, you'll see there's a structure to this. Basically, there's a Hadamard on the first guy, right? And then there's a bunch of X operators that go down here. Well, there could be control Z as well, depending on what the structure of the code is. But right now, for the Steam code, they're just control X operator. Then you apply a Hadamard on the second guy, and then you do some controlled operations from there down to the qubits below it. And then you put a Hadamard on this guy, and then you do this. Right, so exactly how many Hadamards go and things like that, they all go in here. We don't really have to get into details of this. I'm also not arguing why this is correct, but it does work. So basically, you do this, you construct, and you basically look at the standard form and you read off what gates you have to apply. Basically, you're looking at the the entries over here and constructing something. Okay, so you have this. I mean, everything is inbuilt into stack. So you just say, hey, stack, construct the encoding circuit, and then draw it, and it draws it for you. Booyah. Okay. So we can also simulate this circuit, right? So we just say simulate, and oh, so I haven't told you about something very, very important, which is you should have asked me immediately that the psi k goes over here in this case. Okay, so in the last k qubit, so psi goes over here, psi 1 in here, but psi k goes into the last k qubits. So this is the Steam code with k equals to 1. So you only have my logical psi going into the last qubit, but if it was larger, then it would go into multiple of these last qubits, right? So basically, if I simulate this as is, it will give me the 0 state. It will tell me exactly, because I'm inputting the 0 state over here in the last qubit over here. So it tells me that the logical 0 state is this guy. Okay, so these are the bases and these are the amplitudes. If I want to construct a logical 1 state, that's quite simple. There are two ways of going about it. What I do is I swap the last state to, for example, the 1 state by putting an X operator over here and then running my encoding operation. And I do this. Oh, sorry, there is an error here. Sorry, I changed my notation, so it should be number of physical qubits. So I will fix that as well. So you get something like this. You can compare these guys, and, for example, check that they are orthogonal to each other, etc. The other thing that you can do, which makes sense, is that you can first encode your 0 state with your encoding circuit, and then you can apply your logical X operator, right? So at this point, at this dotted line, you have the logical 0 operation. If you apply your logical X operation, which if you remember, was an X on the last 3 qubits, you will construct your logical 1 state, right? So for example, you can check that these two things give you the same result. So all of these things are understood when you do them again, and you should try them with all the different codes that you have seen up till now. So Ron asks which qubits are n and k. So remember that the last qubit, k equals to 1 in this case. So the last qubit here is the logical qubit that we are trying to encode, and obviously n is all the qubits, right? N is not the logical qubit is part of these n qubits that we use to encode the information. Okay, we just take this guy and in place kind of operation where we have zeros everywhere, and this is where we put our psi. And obviously psi does not have to be 0 or 1, right? This is we are just checking. If you want to do psi on some alpha 0 plus beta 1, you can also do that. So you put that in here, and out will pop the psi for that alpha 0 plus beta 1. Yeah. Okay. So just to continue our overview, yeah, so I should give another example just to convince you of this. So this is the 513 code. So if you run the encoding operation for that, for example, I just want to show you that you get both X and Z operations, right? So your Hadamard is followed by some X and Z operations as well. So, and they can go up as well. So they don't have to go down. You just have a Hadamard at different locations, and then you have a controlled operation going up and down from that. So just so you know. Anyway, let's just do the last thing so we can finish in time. So syndrome measurements for stability codes, right? So we also want to know, now that we've encoded, how to detect errors. To detect errors, we have to do syndrome measurements, and there's an algorithm for that as well. What is that algorithm? We have already kind of discussed this. It's exactly what we did for the repetition code, that we measure each of the operators in turn. And the idea is quite simple, that you apply, this is my 7 qubits in which my information is encoded, right? This has experienced some errors, and I want to detect what the errors are. I attach 6 qubits, right? I have 6 generators in my 713 code. So so I'm always using 713 code, right? So m equals to 6. There are 6 guys here. Over here, what I do is I apply a Hadamard on each of them at the start. I apply a Hadamard on them at the end. What I do is I look at the first row. The first row says 1, 1, 1, 1. On the first 4 guys, I apply a controlled X from each of the 4 guys over here. Then the second row says X, right? So remember, these are 0, so this makes it things like nice. But if there's ones here, for example, so I would have Z or Y's being applied here. But this is nice. So I have 1 and 1 and 1 and 1. So I do from the second guy, I do control X's from over here and then over here, right? So that's the second guy. Then similarly, the third guy, that's also some X operator that operates, and the Z operator operates in the same way. So now you have Z measurements happening. So you have these 6 operators that are being measured one by one, and over here you get your syndrome, right? From which you can figure out what the error is. So yeah, I'm done. There's a whole notebook for this as well. You kind of work your way through it, and you can do a bunch of tasks and whatnot, which will help you understand this. Questions? I know I've gone a little fast at the end, but it's what I went through at the end is also the simpler part. So once you do the notebooks, it will become clear. Valerie has a question. It's coming up. Mohammed has a question. Excellent. Yes. Yes. You have noise in your hardware. Yes, I will just update the couple of errors that I just caught, and you can, if you, I'll put it on the QEC thing that a QEC channel when I've updated it, so you can download it again. Oh, thank you, Feroz. I hope you learned some things, and oh yes. So is there Bakao has a question about stack. I'll answer that right now. Is there any other code for which m is not equal to n minus k? That case is so for stabilizer codes, that relationship always holds. There are other types of codes for which, I mean, these things kind of, I mean, can be slightly different, but I mean, for stabilizer codes, this always holds. Okay, let me answer Bakao's question. So he said that I can't sample. So for example, we have let's go here, let's create a console, and I have, right. So let me encode this. So I mean, let's so Bakao, so I have this code, and then you can this is actually stored in encoding circuit, right? So this is exactly my circuit. So you wanted to sample from it, right? And when you sample from it, I mean, in this case, you get what is this? Why is it not sampling? This is the encoding circuit. It should give me something. Am I doing something wrong? Let me just do a simple circuit. Let me write. I'll see what the problem is there. I'm doing something stupid. Just why simple. Let me just do two things and circuit dot append h on the first guy, right? So circ dot draw. This is my circuit. If I do sample, oh, I don't have measurements. That's the problem. I'm like, that's so I have to put a measurement at the end. Yeah. So now my circuit is this, right? So the problem with above thing is there's no measurements here. So now if I do circ dot sample, I get a sample, right? If I do this, these are just printed results. So if you look at the instructions here, so it says return sample and print sample, right? So if I just do return sample true, it will both print them and return the sample, but I can say I don't want to print it, so I just say false. And I do this, and then it has returned an array, right? So I can assign it to some x, and then you can see that x is this a list, and x5 is, for example, false. Sounds good? Okay. Thanks, Ron. Thanks, Carlos. Thanks, Artem. Oh, thanks, Abdullah. Yes, we have. I'm working on it, you know, not a lot of time. Thank you so much for sharing. You are welcome. You're welcome. And thanks, Isma. Okay, I'm glad that you understood things. You're welcome, everyone. There'll be another quiz. You know this, so hold on to the thanks. Until you do that, maybe you'll hate me after it. I hope it won't be too difficult.
Thank you so much, Abdullah. Really
No problem.
great. I think the words from everyone speak for themselves. This is the really last session with Abdullah. Do you have some questions to him? Maybe beyond the content of the 4 sessions?
Yeah, you can ask general questions of any sort.